Okay, we're going to be looking at using tabulated moments of inertia. We're going to use the tabulated ones to calculate an untabulated moment of inertia. And I want you to remember the fundamental idea. Moments of inertia are additive. Let's consider the following. We have a hollow cylinder rotating about an axis through the center. Now we don't know what the moment of inertia of a hollow cylinder is, but what we do know is what the moment of inertia for a solid cylinder is. Now I show here a diagram of a hollow cylinder where the inner radius is R2, the outer radius is R1. Our axis of rotation is, is the center, and it extends into and out of the paper. I show on the right a isometric drawing of the cylinder and the axis of rotation. Now once again, let's suppose we only know the moment of inertia for a solid cylinder, and that's given in the table in your book as I equal to 1/2 mr squared. What is I of the hollow cylinder? Well, we can write that the moment of inertia for the hollow cylinder will be the moment of inertia for cylinder 1 minus the moment of inertia for cylinder 2. And that's going to be equal to 1/2 m1 r1 squared minus 1/2 m2 r2 squared. But that's not the end of the story. We need to arrange this so that we get what the tabulated value for the hollow cylinder is. So what is the tabulated value? Well, the tabulated value for the hollow cylinder is 1/2 the mass of the shell times r1 squared plus r2 squared. Is it the same as the value that I'm looking at right here? Are these two, quote, equal? Well, let's let the mass of the shell simply be mass 1 minus mass 2. And then I can write 1/2 mass of shell plus mass 2, which of course is mass 1, r1 squared minus 1/2 m2 r2 squared. Continuing on with the algebra, I can then carry it out, and I have 1/2 ms r1 squared plus 1/2 m2 r1 squared minus 1/2 m2 r2 squared. Now we're going to do something that is done very often. We're going to add 0. And adding 0 is the same thing as adding 1/2 m2 r1 squared minus 1/2 m2 r1 squared. We're just subtracting the number from itself. Now, putting that into the equation, it seems like all I did was just add 0, but let's rearrange the terms a little bit. What is the quantity given here? 1/2 m2 r1 squared minus 1/2 m1 r squared. Okay. After rearranging the terms, you come out with this equation. That's 0, and so we're left with I equal 1/2 ms r1 squared plus r2 squared. And these two values, the tabulated value and this value, are the same. So I can come over here and I can say these two are equal. So all I did was subtract the solid cylinder at radius 1 moment of inertia from the solid cylinder at radius 2 moment of inertia to get the moment of inertia of the hollow cylinder. And this general principle can be applied to most moments of inertia we want to obtain just by using the tabulated ones. End of module.